Welcome to This Explainer. Today, we're not just messing around with basic prompts or tinkering with simple APIs. No, we are going to build a state-of-the-art enterprise LLM platform from the absolute hardware up. Using a highly detailed principal architect interview guide as our blueprint, we're unpacking exactly what it takes to serve generative AI at a massive scale without breaking the bank or, melting your servers in the process.
Let's kick things off with a pretty counterintuitive question directly from our source material. When people think of AI hardware, they usually obsess over raw compute power, the massive flops you need to train a foundational model from scratch. But for inference, the actual day-to-day running of that model in production, why is the physical speed of your memory bandwidth actually way more critical than raw math crunching ability?
Well, the surprising answer here is that data movement is your ultimate bottleneck. In LLM inference, the system is constantly dragging massive model weights and the KV cache out of memory for every single token it generates. It's literally like having a lightning-fast, world-class chef in your kitchen who spends 90% of their time walking back and forth to a faraway fridge just to grab ingredients. Moving the data physically limits your system long before your processor ever runs out of compute power.
So here is our roadmap for the explainer today. First up, the memory bottleneck. Second, optimizing serving engines. Third, the inference gateway. And finally, building enterprise platforms. All right, section 1, the memory bottleneck. Let's start at the microscopic level and tackle the physical constraints of our architecture. To really wrap our heads around the hardware layer, we got to talk about arithmetic intensity. Think of this as the ratio of actual math being done compared to the amount of memory being accessed. Because LLM inference involves reading gigabytes of data just to perform relatively simple matrix multiplications, it has a very low arithmetic intensity. It's fundamentally memory-bound. This is exactly why tossing standard CPUs at this problem fails catastrophically, and why highly specialized hardware is absolutely non-negotiable for enterprise workloads.
And that brings us right to the silicon itself. When you stack up workhorse chips like the H100 against the newer B200, specifically for LLM serving, you're looking at a massive architectural shift happening in real time. The B200 is built specifically to attack this exact memory bottleneck. By providing significantly higher memory bandwidth, larger raw memory capacity, and targeted transformer acceleration, it radically alters the economics and the performance ceiling for these large-scale inference workloads.
But, just throwing faster metal at the problem, that's only half the battle. We need brilliant software to match it. Enter PagedAttention. Historically, KV cache, which stores the context of past tokens so the model can remember the conversation, suffered from terrible memory fragmentation. It just wasted incredibly expensive GPU RAM. PagedAttention solves this brilliantly by treating the KV cache exactly like standard virtual memory in a computer's OS. By chunking KV blocks into fixed-size pages and dynamically routing them through a page table, it practically eliminates wasted space, which lets you cram vastly more concurrent requests onto a single GPU.
Still, we can't ignore the laws of physics. As user context length grows, say somebody drops a massive 100-page financial report into the prompt window, it totally amplifies our constraints. Suddenly, your KV cache memory usage explodes, latency spikes, GPU utilization redlines, and ultimately your cost per inference goes right through the roof. You can't just offer infinite context windows to your users without paying a really heavy architectural price behind the scenes. Okay, moving right along to section 2, optimizing serving engines. Now that we've navigated the hardware traps, let's move up the stack to the software layer.
At this layer, your make-or-break decision is choosing the right serving engine. And spoiler alert, there is absolutely no one-size-fits-all here. If your main goal is getting the absolute highest throughput and maximizing that KV cache efficiency we just talked about, VLM is typically your best bet. If you need a rock-solid, production-ready solution deeply tied to the Hugging Face ecosystem, TGI is your go-to. For complex routing, advanced scheduling, or strict structure generation, SGLang shines. And if you're orchestrating massive, distributed AI pipelines across an entire cluster of machines, RayServe is the heavy lifter you need.
Now, if you want to push performance to the absolute bleeding edge, the most advanced platforms use what's called a disaggregated serving architecture. Think about how text generation actually works. It has two distinct phases. First, there's the prefill phase, a heavy, one-time parallel computation to understand the initial prompt. Second is the decode phase, a sequential, memory-heavy process of spitting out tokens one by one. Because these two phases require completely different compute profiles, disaggregated serving physically separates them onto entirely different, specialized infrastructure layers. This lets you independently scale and optimize them.
So how do you optimize those layers? Well, it depends entirely on your target user experience.
If you're building a real-time customer support chatbot, your absolute North Star is minimizing latency for that very first word, what we call time to first token, or TTFT. To force this number down, you've got a specific toolkit. Relentlessly reduce initial prompt links. Aggressively utilize prefix caching so you aren't recomputing standard instructions. Apply prompt compression. Use incredibly fast tokenizers and dedicate heavy compute solely to that pre-fill phase. On the flip side, what if you're running massive offline data extraction jobs where nobody is sitting around tapping their foot waiting for a reply? Now your North Star totally shifts to overall throughput, tokens per second. Your toolkit entirely changes. Here, you leverage continuous batching to keep those GPUs completely saturated at all times. You rely heavily on PagedAttention, deploy speculative decoding to actually try and guess future tokens to speed things up, and use model quantization to shrink the memory footprint. This lets you push a massive volume of requests through the system simultaneously.
Which brings us to Section 3, the Inference Gateway. With our engines humming, we need an air traffic controller to manage the chaos.
Because here's the reality. Enterprise platforms are incredibly fragile if they just rely on a single model. If you're bouncing traffic between external giants like Bedrock, OpenAI, or Gemini, having a robust fallback sequence is literally your lifeline during an outage. You place an abstraction layer in front of the user, constantly monitoring the health of downstream APIs. Say OpenAI suddenly goes down, your gateway executes intelligent routing and immediate failover to Gemini. Then, it normalizes the API response format on the way back. Your end-user application seamlessly keeps working without ever knowing a massive outage just happened behind the scenes.
But what about during normal, healthy operations? How do you decide exactly where to send a specific prompt? The answer is cost-aware intelligent routing. And let me tell you, it can save enterprises millions of dollars. When a request hits the gateway, it dynamically estimates the complexity of the task. It looks at strict domain requirements, checks the user's subscription tier, and evaluates latency SLAs. Then it instantly routes the prompt to the absolute cheapest, smallest model statistically capable of meeting your quality bar for that specific query.
This kind of routing forces every principal architect to face a classic dilemma: hosted APIs versus self-hosted models. Relying on hosted APIs gives you blazing fast deployment and near-zero operational burden. But you sacrifice ultimate control and open yourself up to unpredictable, incredibly high long-term scaling costs. On the flip side, self-hosting your own open-source models gives you crucial data sovereignty and predictable profit margins, but you take on massive infrastructure management and super steep upfront GPU costs.
Regardless of where these models actually live, you absolutely have to benchmark them rigorously, and this gets especially tricky when you're comparing newer mixture of experts, or MOE models, against standard dense models. Because MOE models only activate certain neural pathways per prompt rather than firing up the whole brain, you can't just look at a single metric like parameter count. You have to run holistic, continuous evaluations across task-specific quality, peak throughput, latency jitter, GPU utilization, and operational cost, all using standardized, blinded benchmark datasets. And hey, when your benchmarks show it's finally time to upgrade a model in production, you absolutely do not just flip a switch. No way. To protect the enterprise, you've got to execute canary deployments. You silently route a tiny fraction, say just 1% of live traffic to the new model version. Then you obsessively monitor it for regressions. Are latency metrics slipping? Is the automated hallucination monitor spiking? Only after it passes both automated tests and strict human spot reviews do you gradually dial up the traffic to the new model. All right, final stop. Section 4, building enterprise platforms. Let's zoom all the way out past individual models and gateways. When you're designing for a global enterprise, the stakes completely change. You are now serving multiple business units simultaneously, which means you need ironclad governance and tenant isolation. If you get this wrong, highly sensitive HR data could leak straight into engineering's code generation chatbot. This requires strictly enforced role-based access control, entirely dedicated vector databases for different departments, unbreachable routing policies, and really granular cost tracking, so you can accurately charge back those heavy GPU compute expenses to the right people.
And then, of course, there's the classic noisy tenant problem. You know, like what happens when the legal department decides to run a massive million-document batch processing job right at 2 p.m. on a Tuesday. If left unchecked, they will steal all the compute and slow down the real-time customer-facing chatbots to a total crawl. To survive this, you've got to deploy strict isolation tactics. You apply dynamic rate limits, enforce workload prioritization rules, and utilize tenant-aware scheduling with dedicated capacity pools. That ensures one department's sudden spike never takes down the platform for everyone else.
So, stacking all of these meticulously designed building blocks together, we arrive here. This is it, the ultimate production-grade architectural blueprint. You've got a shared AI gateway and model router intelligently handling external and internal traffic, specialized RAG services, and agent platforms providing the actual business capabilities, all resting safely on top of a bedrock of rigorous observability and governance layers. This is how you confidently support finance, healthcare, legal, and customer support on a single, global, multi-cloud platform.
We've covered a tremendous amount of ground today. From the fundamental physics of GPU memory bandwidth all the way up to multi-tenant enterprise governance, you now hold the blueprint for building a resilient production-grade LLM platform from the hardware up. But here is the final provocative thought I'll leave you with. In a future where every single one of your competitors has access to the exact same foundational models, is your platform's underlying architecture actually your only remaining competitive advantage? Thanks for joining me on this explainer, and keep building.